Welcome to the Journey Chez Chem. Well, today's warm-up, we're starting something new, and I'm using some of the things that you already know. Electron dot diagrams. So do the best you can, and I'll see you in a moment. In number 1, we are going to be getting the dot diagrams. And we had this very early on. It is the outermost electrons. And when we look at the periodic chart to review, everything in the first column is S1, and therefore it has 1 valence electron and 1 dot. Everything in the second column is S2, therefore it has 2 electrons and 2 valence electrons and 2 dots. Then we have S2P1, and the dots are the S and the P electrons only. Therefore, we have 3 dots. Then we have S2P2 and 4 dots. S2P3, 5 dots, 5 valence electrons. S2P4, 6 dots, 6 valence electrons. I ran out of space. That's okay. I'll just add a little on. Then we have S2P5, 7 dots, 7 valence electrons. And finally, we have S2P6, 8, our octet, with 8 electrons, 8 valence electrons. However, we do need to remember that on the top here, for helium, it is S2, and therefore it only has 2 dots. And hydrogen only has 1 dot. And in the first energy level, we can only have a maximum of 2 electrons in that first energy level in the s orbital. Therefore, I can then look at the periodic chart and determine the number of dots. Oxygen is S2P4, therefore it is 6 dots. Now I'm going to be writing my electrons as circles or as X's in order to show very clearly my electrons. Hydrogen has 1 dot, S1. Fluorine has 7 electrons and 7 valence electrons. Sodium has 1 dot, it's S1. And fluorine was S2P5. Sulfur is S2P4, like oxygen, and therefore it has 6 dots. Finally, nitrogen is S2P3, and it has 5 dots. Now, in some cases, some instructors do like for you to put them in a specific order. However, that's not a priority for me. I just want you to know the number of dots that each one has in its valence outermost shell. In number 2, it asks for the difference between a formula unit and a molecule. A formula unit is an ionic compound where the electrons are transferred, and a molecule is a covalent compound where the electrons are being shared. And what we're going to be talking about during this topic is nonmetals and nonmetals that are sharing electrons. Molecules are composed of nonmetals and nonmetals. And that's what we're going to be doing. And we're going to talk about the different shapes that molecules will have. Now we are talking about nonmetals and nonmetals. And everything that we are talking about is shared pairs of electrons and bonded pair of electrons. So bond pairs are pairs of electrons that are between 2 atoms, and lone pairs are around the central atom but not shared with another atom. So they're called lone pairs. And the first one that we want to discuss is carbon dioxide. We have carbon dioxide. Oh, no, 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 no. Carbon dioxide. Now, the first element is always in the center, and I didn't want to jump ahead too much because you need to go with it as a pattern. Carbon dioxide. Carbon is in the middle. 1, 2, 3, 4 valence electrons, and oxygen has 6. And I am going to need to double bond those oxygens in order to get an octet. We always want an octet for all of the shapes that we are doing today. Now I want to circle my octets to make sure that I got 8 electrons around each atom. And therefore I have 8 around the carbon and 8 around each oxygen. Now we have what is called a line diagram or a line structure, and for each pair of electrons we have one line, and therefore it looks like this. And when I look at this molecule, I look at the pairs of electrons, and it's as though carbon is where my hand is, and balloons work really well for this. And I'm so excited I get to play with balloons, and you might want to do this at home too, because they naturally will go into this shape. And when I look at this shape, ooh, okay, here we go. Those little pesky fellas, they just try to get away. We won't let them get very far. I just have to be a little tighter with them. Okay, don't worry, we'll get it. So here we have the shape. Here is one of the nuclei, and here is one of the nuclei. And when you look at the geometry of the shape, it is a straight line. And therefore, this one is called linear. Linear. And we had, when we look at it, a double bond counts as one bond pair. So we have 1, 2 bond pairs, and there are no electrons above the central atom that are just floating there. Therefore, we have 0 lone pairs. Now we also need the angle, and I always want to write angel, but I have to remember that it's angle, and then we have our example. And the angle of a straight line is 180. And our example was carbon dioxide. The next one that I'm going to do is SO3. Sulfur is in the middle, and it has 6 electrons. Oxygen also has 6 electrons. Now I always put the electrons on the outside, and I use X's and O's because I want to know where those electrons came from, which atom. And therefore I'm going to put the 6 around this one, and I know that I need 2 more electrons to get my octet. Therefore I'm going to make a double bond. And that way I get 8 electrons around every one of them. I have 8 here, 8 here, and here, and here. And it looks like this in the line diagram. And I could have drawn this double bond on any of these 3 oxygens. I could have picked any of them. Therefore, there's 3 possible diagrams that we could have here. And when we have equally valid diagrams for the same molecule, we call them resonance structures. These are, every one of these, if I was asking for a line diagram of SO3, any of these 3 would be fine. And notice that this is not sulfite, otherwise it would have to show a -2 charge. This molecule could be drawn any of these 3 ways, and therefore they are resonance structures. And the actual molecule is not a double bond and 2 single bonds. It is actually a 1 1/3 or 1 1/2 bond. It's not exactly, because it's an average of these 3 diagrams. And because this is a 2-dimensional representation of a 3-dimensional thing. Well, let's take a look at this 3-dimensional thing. Well, I'm going to use the pink ones. So I'll take 3 balloons here. 3 balloons. I just have 2, but I'll get another one. And when I put the 3 balloons together, I know you want to do this at home. I bet you're going to run out tonight and get some balloons. And I let them fall into their natural position. You can see that it looks like a triangle. And notice that the triangle is on a plane. It's in a single plane. And therefore, we call this trigonal planar. Trigonal planar. Trigonal planar. And when we look at the diagram, how it was, it had 3 bond pairs and no lone pairs. And when we see the structure was like this angle here is 120 degrees. The next one that I'm going to do is ozone. Ozone is O3. Oxygen, of course they're all 3 oxygens, it doesn't matter which one's in the middle. Oxygen has 6 valence electrons. And this oxygen has 6 valence electrons. And this oxygen I need to double bond so that I get my octet. And then I have my octet around everything. 8 around here, 8 around each one of the oxygens as well. And if I were drawing a line diagram, it would look like this. Now, because I could have put the double bond here or on the other side, that is a resonance structure. And when we look at this, I'm going to use this pink one as my lone pair. And when I add the lone pair in here, there is repulsion. All of this is all about repulsion of electrons. And it's going to cause these 2 to take a bent or angular shape. And therefore we call this bent 1. I call it bent 1 because it has 1 lone pair. And that's what I call it. And I guess that's what you'll call it too. So we have bent 1. Bent 1. And bent 1, we had this structure. And we had 2 bond pairs and 1 lone pair. And that lone pair is not attached to another atom. It's lone. It's unshared. And that would be 117 degrees. Now, the next one that we're going to do is methane, natural gas. We like methane. It's CH4. Carbon has 4 electrons, and each hydrogen has 1. And that one was pretty straightforward and easy to get. So I have my octet here, and then I have my 2 around for each duet for my hydrogen, and I get a structure that looks like this. Now, this is called a tetrahedral. Tetrahedral. And we had 4 bond pairs and no lone pairs. And the angle is 109.5. And that's been measured, and we know that that's what it is. If we look at the balloons then, and we get rid of the purple ones because we want it all in pink. Pink, pink, pink. Pink, pink, pink. You just gotta love balloons, don't you? They just have some fun with the balloons. And I can do this. I've had practice at this. Sometimes it works better than other times, but today's a special day because we're talking about it. And here's the challenging one. We have that 4th one that we have to get in here. I'm going to get it in there, and they're all going to stay together, and then I just turn them around and round and round, and then all of a sudden, it's in my shape. And notice that each one of them is not opposite of the other. And in my diagram, oftentimes it looks like one's on top and one's on bottom, but that is not the case. They are not opposite of each other, no matter how I look at it. That is the tetrahedral shape. Okay, we only have 2 more to do. Well, the next one is ammonia, NH3. Now, nitrogen has 5 valence electrons, and hydrogen has 1. Now that worked out pretty well. We have 8 around the nitrogen and a duet around each one of the hydrogens. Oh, I don't want black, I want red. And here we go, hydrogen, hydrogen, hydrogen. And what this looks like is nitrogen with the lone pair and 3 bond pairs. We have what is called trigonal pyramidal. And it has 3 bond pairs and 1 lone pair. And the angle here is 107. Now, this next one is one of my most favorite, and it's important for you to know. It's water. And water, oh, I needed to show you what this one looked like. Here we go, we're gonna get rid of one, oh, we got rid of one of the pink ones. And we'll get a purple one. We'll put the purple one on here. And now the pink one's trying to escape. No escapees allowed. Out of here. Just gotta put them to rest. Ah, now here my lone pair is pushing these others down, and therefore we get this 107 angle because my lone pair is very big electron cloud and the others want to get away as much as possible. So it becomes what we call trigonal pyramidal. Finally, the last one is water. And water is H2O, and oxygen is in the middle. And oxygen has 6 electrons, and hydrogen has 1. Now, it looks on my diagram that the lone pairs are above and below because we're talking about a 2-dimensional diagram here. But you remember, we said that it is not like a 2-dimensional. And when we look at this, oh my, I'm actually kind of sad because this is going to be the last time I'm playing with these balloons because we're almost done with the chart. But I have to also get rid of, ooh, one of the pink ones. And so I need 2 pink and 2 purple. It's a good thing I color-coded them because the purple are my lone pairs and my pink are my bond pairs. And here's another lone pair, and she's running them around and around. There you have it. We have 2 lone pairs and 2 bond pairs, and you can see this is a bent or angular shape. It's called bent 2. Bent 2 because we have 2 lone pairs. Bent 2. Now, that's very, very important. We had 2 bond pairs and 2 lone pairs and a 105 degree. And when we draw the structure here, we have the 2 lone pairs and the 2 bond pairs, in our line diagram, and you need to insert that into the chart that you wrote up today. And you can see that it didn't matter. These lone pairs are always going to go on one side. They're not going to go at top and the bottom because of the way the shape is. It wouldn't go to the bottom. I could force it into the bottom. Look, I'll try. I could try to force it, but look, it just goes right back up on the same side. So no matter how I turn it, those lone pairs are going to be on one side or the other. So that was some fun. We learned all about the 6 shapes that follow the octet rule. And tonight you get to practice drawing some of these shapes. I know you'll have fun doing it. I had fun doing it, and I can't wait to see you tomorrow. Bye.